מילה, לא שומעים אותך, את במיוט.
סליחה, תודה. אז ערב טוב לכולם, תודה רבה שהצטרפתם אלינו הערב. אנחנו שמחות לפתוח את הוובינר העשירי של MeDS. הנושא שלנו הערב זה סקירה של עולמות הדאטה סיינס בבריאות הנפש. זה וובינר שלקח לנו הרבה זמן להגיע אליו, במקור הוא תוכנן במסגרת האירועים של אוקטובר, שכמובן לא קרו, ואחר כך ניסינו להרים אותו באפריל, וסוף סוף אנחנו שמחות שאנחנו התכנסנו לכאן הערב ולשמוע את אנדרי, שתכף אני אציג אותו. אבל לפני כן אני רק רוצה ככה להגיד שאנחנו במסגרת אירועי מאי, שמאי הוא חודש מודעות לבריאות הנפש. יש לנו עוד אירוע שאנחנו מתכננות ב-19 במאי, כבר תשריינו ביומנים, אנחנו ממש היום מחר נפרסם אותו. זה אירוע שהוא בעיקרו נטוורקינג, מינגלינג, אבל גם יהיה פאנל מקצועי מאוד מאוד מרתק, גם מטופלים, גם קלינאים, גם אנשי דאטה, בנושא פוסט-טראומה. אז יהיה מאוד מעניין וכמובן אקטואלי לכולנו לדבר על הנושא הזה ולשמוע על דברים מאוד מרתקים שקורים כרגע בתעשייה בארץ. זה ככה הודעות מנהלתיות. כמובן תמשיכו לעקוב אחרינו, הקלטות של האירועים שלנו מפורסמות בערוץ היוטיוב שלנו, פשוט MeDS Medical Data Science. ואני שמחה להתחיל את הערב ולהציג את דוקטור אנדרי קורמיליצין, שהוא חוקר בכיר במעבדה באוניברסיטת אוקספורד ובמחלקה לפסיכיאטריה, ואנדרי והצוות שלו חוקרים מגוון תחומים בבריאות הנפש, כמו שהוא יספר לכם, מתעסקים במגוון אלגוריתמים ליישומים בעולם האמיתי של מחלות נפש. אז אנדרי, תודה רבה שהצטרפת אלינו מאנגליה, והבמה שלך.
תודה מילה, אני ממש מתרגש להיות, בדיוק כמו שאמרת, ניסינו לעשות את זה כמה פעמים וסוף סוף, שזה מצליחים לעשות את זה, תודה על ההצגה. כן, אז אני אתחיל לעשות, נציג את הסליידים. מה אתם רואים? אתם רואים את הסלייד או את הפרזנטר מוד, או את הסלייד
רואים את הפרזנטר מוד.
כן, נכון. אחת. כן. ועכשיו אתם רואים את הסלייד המלא, כן?
עכשיו רואים טוב.
כן, יופי. כן, כן, פשוט יש כמה מסכים וזה כל הזמן קופץ אחד משני. טוב, אז אני אעבור לאנגלית כי זה פשוט יותר נוח וגם כל המושגים, אבל באמת פשוט תעצרו אותי, תשאלו אותי שאלות, אני אשתדל לענות. Well, so let's start. And the first, there are some disclaimers. So these are different research grant I hold, so from different funders, including pharmaceutical companies. And so the plan for today, it will be pretty informal. As Mil mentioned, I will give a rather wide overview of what can be done or how learning algorithms could help in mental health. So mental health is a really huge area as like a physical health, as you may know. So it encompasses a lot of different ideas, including, for example, a brain, and also it collects a wide range of data, including structured and unstructured fields. And I will delve into different aspects and we'll discuss. So the informal plan for today is, first of all, we discuss about mental health. Overall, why is it important for us and why it's important to keep our mental health healthy and shape. I will go over a bit of a historical overview of applications of learning algorithms from early 50s and 60s. And then I will I will discuss why mental health data is primarily given in a narrative or free text form. And then I will touch upon a bit of a big data paradox. And I will conclude with the ethical consideration of modeling and why involving patients and public is quite important in research and overall in developing algorithms and systems. First of all, I will right. So mental health is really wide. So well-being as physical health, and however, it often receives less attention and priority in our personal life and society. So ultimately, the state of our mental health directly impacts our everyday aspects of life. So, for example, the quality of relationship with others, or work performance, and of course, physical health. So, healthy mental state also helps create positive relationship and social interactions, which are quite important for our to achieve our personal goals and enhance our ability to communicate effectively. And so good mental health is crucial for achieving a high quality of life. It enables resilience and the face of adversity, as Milo already mentioned. So mental health is really important, but often overlooked and less has attention. And I will discuss later some reasons, but in some cases there is a stigma of mental health or stigma of having mental disorders, as well as lack of mental health data because of high sensitivity compared to some branches of physical health. Some examples of mental disorders, they include mood disorders, anxiety disorders, personality, neurodevelopmental disorders that affect the development of our brain, eating disorders, and so on and so forth. The Holy Grail, or the sacred book of mental health disorders, is ultimately called the Diagnostic and Statistical Manual of Mental Disorders, or DSM in short. In its latest reincarnation, it's in the fifth version, which was expanded, revised. So every edition is being revised and updated. However, some clinicians and researchers believe that hard diagnostic categories may be suboptimal in order to describe the complexity of mental health. So a new way of looking was proposed, such as a transdiagnostic approach. A transdiagnostic approach, as its name suggests, in psychiatry is a framework that focuses on shared mechanisms of all processes underlying multiple mental health disorders, rather than treating each disorder as a distinct and a separate entity. So, for example, a good example might be as an autism spectrum disorder, where people initially thought it could be divided into strict different beings, and then just realize there are so many shared features across different presentations, so it is better to speak about a spectrum. The mental health, probably it is we don't see lots of information on mass media somewhere, or like headings. That, however, there is a silent crisis on mental health, and it is becomes more and more prevalent, and especially there have been lots of published literature about the effect of COVID on both on mental health, the impact of COVID first from the societal point of view of people being alone at home, so how it could affect people being locked down at homes, especially elderly or young people. But the second is the mechanistic, what COVID did to our brains, kind of a brain fog or other long COVID approaches effects. So there is a mental health crisis, but it's a silent crisis because, as mentioned, mental health, it is quite an unpopular disorder, if you wish. And so according to World Health Organization, so quite a lot of people are affected by depression. So depression is highly prevalent across many countries. Many people diagnosed with anxiety disorders. And sorry, can I ask some people? I think there are some unmuted participants who have some background noise. If I can please ask to mute. Great, thank you. And as you may, so those who involved in autism research, it is not surprising that the number of children, especially children being diagnosed, or those who meet the diagnostic criteria for autism, is increasing and has increased drastically over the years. So it means that there is a lot of what we as data scientists and algorithmic people, we can offer and help mental health area. So before we go into more contemporary and nowadays algorithms, so let's start with some quick historical overview what has been done, because algorithms, it is not specifically to late 2000 or to neural networks. So statistics has evolved, and computational algorithms, they have been evolving since the 1930s, where so as you can see, this very oversimplified timeline, how the computational approaches have evolved. So starting from elementary circuits, logic operators, and machine translation in late 50s or late 40s, it was pretty much a rule-based methods, to sophisticated rule-based chatbots and early learning algorithms, such as the Rosenblatt's perceptron. The Rosenblatt perceptron, it was developed in the late 50s, so which is a basis to some extent to our modern neural networks. Interestingly, in early 1960s, clinicians have realized the potential of such technologies to attempt to use them as an assistive technologies in their clinical practice. And it brings us to one of the very first chatbots developed by Joseph Weizenbaum. So one of the earliest example, it was developed and it's called ELIZA, which simulates dialogue between a human and a Rogerian therapist. It achieves this approach by capturing certain lexical and syntactic structures in a typical Rogerian style interaction, or like a therapist-patient interaction. And then pattern matching to rules, extracting subject and object to sentences, and then replying with a question that seems consistent with what a Rogerian therapist might do. There was a funny story that Weizenbaum reported in his 1967 book, Computer Powered and Human Reason. So his office assistant was so convinced that there was a sensitive and empathic therapist at the other end of the teletype terminal, so it would use the old style terminals. And so she would shut the door between their offices during lunchtime so she could converse privately with Eliza. I don't think Eliza could pass the Turing test back in time, but it was developed in such an empathetic way that some people were convinced. And so the important take home here is that the conversational program appears to be having a meaningful conversation, but is just following relatively simple and prescribed rules. So so later in 72, when this statistical learning algorithm, they start appearing, and after the publication of DSM, the second edition in late 60s, Fleiss and his group took a sample of over 700 patients and looked at their symptoms and how they corresponded with diagnostic categories. So it was early days of data collection. It was perhaps done on a pen and paper. Apologize. And then later, so the clinician, they asked for different symptoms, and then this group of patients, they've been diagnosed in according to DSM-2. So they look at 11 categories, and they tried 3 different algorithms and I'll talk in a second. But please note in the table, the best performing algorithm is called Diagnose2. So the method they used were as follows. They used what we now call, so they used three methods, as I mentioned. The first one, what is called a linear discriminant analysis, where you project all your features, all your patient's symptoms, constellations onto space, and try to find a line that separates different diagnostic criteria. And so it was quite novel in the 70s. The second method used what we call the bias method, or what we now call naive Bayes classifier. That the classifier uses probabilities of certain symptoms belonging to certain diagnoses, so that if I give you a new patient, your job is to compute the probabilities of 11 diagnoses. Then, given a new patient with certain cluster or constellation of symptoms, you will be able to predict or provide probabilities of having such diagnosis. So the bias method is statistical. Discriminant analysis is also statistical, but the method that outperformed both was based on a decision tree. And if a certain symptom is present, then you go either left or right, and then you go down the branches, and you will be asked another question. So if the patient is younger than 45, then eventually you arrive at the diagnosis. So it was a hybrid approach of both a rule-based and a statistical methods. And nowadays, so I wanted to bring some of the examples that specifically our lab was involved in certain projects in the Department of Psychiatry in Oxford with lots of clinical and engineering collaborators. So nowadays, contemporary machine learning algorithms and hardware specifically allow for more sophisticated solutions. So these are some examples. So on the left-hand side, so probably I will take a laser pointer. On the left-hand side, with Oxford, we developed a True Colors platform to monitor the mood of patients diagnosed with bipolar disorder. It was developed in 2014, and it is so the platform, so we collected self-reported data from patients about their mood. Patients complete the online clinically validated questionnaires assessing their depression and mania levels on a weekly basis. So they've been prompted, they could have used a web interface or on a phone. And this creates a longitudinal trajectory of the patient's mood across a number of domains. So for example, sleep quality, mood, appetite, suicidal ideation, social involvement, and many others. And then we applied machine learning methods to time series and sequential data to estimate early onset of certain conditions, such as depressive or manic episodes, to evaluate a mood variability and correlate with certain clinical evaluated outcomes and other predictive downstream tasks used, which clinicians found useful. So it was a really collaborative close work with clinicians. In another occasion, we were looking at correlating or capturing facial expression using a smartphone camera with mood. So it is work in process, but basically so we took 7 fairly standard categories of facial expression, of emotions, like happiness, surprise, contempt, sadness, fear, and then we also collected data. We asked, so during this clinical trial, well, the study, not clinical trial, there's a study, we asked patients and also healthy volunteers to perform certain tasks on a computer. So pretty much standard clinical evaluated task, and during the tasks, we captured the facial expression. So we were able to associate the facial expression not only mood, not only emotions, but also patterns of facial expression to mood. So we were because this task, they were able to capture some clinical features. In another project, which is led by our colleagues, colleague clinicians, we designed a tool which is capable of prescribing depressive. It's called Petrushka, led by Professor Andrey Kormilitzin and his team, a consultant psychiatrist and professor of psychiatry. So we were involved from the technical perspective. An idea was how to choose the right antidepressant and prescribe to the right person, given some personal preferences. So, for example, different medications such as antidepressants, they may cause different side effects, and people could choose what they could choose what they're happy to accept or what they're not happy to accept in terms of side effects. And now this project heavily unfolded into bigger, and if you Google, it's called Petrushka or Andrey Kormilitzin. I can put a link on chat. So he leads a large team of precision psychiatry in our department. And on the right-hand side, we took another route. It was a project where we used a large collection of free text, electronic health records from secondary mental health. These are progress notes from patients written by psychiatrists, and we applied NLP and text mining methods to extract information from free text about side effects of certain drugs and rating scales of cognitive impairment. So this project was in the context of dementia, and we studied what drugs people have been prescribed, and we wanted to see whether we can find patterns that are associated between the drugs and the rate of cognitive decline. So what you can see here, so if you follow the standard guidelines, clinical guidelines, the cognitive decline will drop more sharply. And the neural network was able to find certain combination that would slow. Of course, we cannot treat dementia. It is untreatable as of today. There are potential drugs, but perhaps if we can mine lots of information from large biomedical data sets, we can find certain combination drugs that work for certain people, given their personal characteristics, that can slow down the rate of decline. And so, speaking of electronic health records, now it brings us into the area of natural language processing and text mining. And I'm going to, for the next several minutes and slides, I will delve into why mental health is predominantly written and narrative form. So NLP and text mining methods, and especially now LLMs, large language models, are one of the most widely used tools and methods applied to observational data. So disorders of the brain are largely expressed through language and behavior. So clinicians usually assess the patient's mental health condition through interviews and discussions. And as a result, patients' data in mental health is largely collected as free text clinical narratives and embedded with language, behavior, and subjective experiences. So these free text notes are often non-standardized, making it challenging to extract information using traditional methods. So this is where the natural language processing and text mining methods, they shine, and they can unlock rich information contained within these unstructured clinical notes. So applying NLP methods and to EHRs, we can derive insights about symptoms, rating scores like the treatment trajectories, symptom trajectories. We can study longitudinal, cross-sectionally, and potentially identify risk factors and early warning signs. And of course, hopefully, we believe we can use this tool to improve outcomes for patients and help clinicians to extract information from large data. However, it is very tempting to apply NLP and text mining method directly to mental health, electronic health records. However, one of the key difficulties in applying such tools is that the mental health care is inherently vague and subjective nature of the language used to describe mental states and symptoms. I'm not a clinician. I cannot compare directly to, so for example, how cardiologists or other clinical specialties, they write the clinical notes, I would assume there is some commonality in the training. However, mental health and what I've learned from my clinical colleagues and psychiatrists and clinicians, so the language is quite vague. So here, for example, an example of where you have an interaction between the time of a recording of, so for example, mental health examination and clinician that recorded. Just imagine there were 3 different clinicians. It could be a consultant psychiatrist, it could be say, a mental health nurse, and a trainee, or a new, for example, like a medical student who was writing or reviewing. So on the assumption that the psychiatrist sees a patient 6 weeks ago, another colleague sees the same patient 4 weeks ago, and the third, it could be trainee and the patient today. So clinicians would usually record their observation like that. And so the first clinician would mention the mood was low, for example, 3 out of 9 on some abstract scale. The second clinician would say mood stable, whilst the third clinician would say mood is unremarkable. However, what does it mean stable in this context? So if the mood was low and now it's stable, does it mean that the mood remains today 3 as it was 4 weeks ago, or the patient is euthymic? Or does it mean that there is no notable difference or change between week 6 and week 2, and today's mood is unremarkable? Is it unremarkable compared to 6 weeks ago or to 2 weeks ago? So these are very small, one of the large spectrum of complexities we face when we apply NLP and text mining to mental health clinical notes. So vague language poses additional challenges to NLP methods. So and by the way, including LLMs to extract clinically meaningful and helpful information. So now what I will do, I will review both the classic and a well-established NLP techniques applied to mental health and challenges, as well as more interesting and novel, large language models and the challenges we face. So these are so usually if you're an NLP person and you're given a problem to extract, for example, develop an information extraction tool, you would always start with developing an annotation schema. An annotation schema, it is a set of rules, prescribed rules, or agreed upfront before you delve into the project, where you decide on what you're going to extract, how you're going to annotate different concepts and different entities. So, for example, given a annotated text such as a patient was prescribed fluoxetine 20 milligram daily for 8 weeks for low mood, you would sit down with clinicians and you would all agree on that clinicians are interested in extracting drug names, the strength of drug, frequency, duration, and symptoms. And then you would sit down, you would train a bunch of clinicians to annotate documents to design your training and consequently developmental text and test data sets. And so some of the techniques we usually use, what we call classical techniques, are named entity recognition, relation extraction, text sentence classification, negation detection, and many more, which are conceptually similar. I will not delve exactly into them because they will just take another hour of seminar, and some of them may be well experienced in such methods. So these methods, so basically you train models. They could be both rule-based models where you create ontologies with some fuzzy pattern matching. You can use regex, regular expression matching, or you can use statistical models such as a seconds to seconds modeling, and to predict. So you learn, you tokenize your text, you split into tokens, into words or into subwords, depending on your technology, and then you predict the category each of your token word belongs to. So here, for example, this word belongs to fluoxetine. And this corresponds to a dose. Then you start classifying the relationships between them. It is helpful to then you can build a knowledge graph because you can connect different entities. So for example, if you have multiple drugs mentioned in the same clinical note, you obviously want to associate the right dose to the right drug name rather than just saying, oh, I've got 5 drugs mentioned and some 5 doses. And of course, and negation are quite also important because the way how clinicians use the right text, they could say, so for example, the patient denies hallucinations, or for example, denies some symptoms. It means the patient doesn't have. Usually clinicians will not list all possible things that are not present, and I will speak about this briefly later. However, in some cases, it is quite reasonable to expect that clinicians will mention something which is not present, probably because it was present before, and now to mention that, for example, the patient recovered and there is no presence of certain conditions. And obviously, the main approach, the main rationale of designing such information extraction system is to structure unstructured text. So, for example, we can parse clinical notes, we can take a trajectory, we can take a chronologically ordered clinical notes from patient, and then we can extract information from each note and build a timeline of patient's health. This is totally made up examples. And we can then visualize. I'm sure there are lots of startups and approaches and dashboards that do this quite nicely. And also on the right-hand side, we can then structure and extract in a tabular form, such an Excel spreadsheet, and then we can give it to statistician or to epidemiologists to run studies. So, for example, to understand or to study the prevalence of certain symptoms, or whether like pharmacosurveillance, where to study how different drugs they have been prescribed, under what condition, whether they've been misused. So, for example, some opioid, whether they've been prescribing and there is some problems with prescriptions. So the information extraction plays a crucial and integral role in research and tools. So these are, just to make things a bit more concrete, these are some examples of what our group was working on. On the left-hand side, the project which is called ChronoSeq, which stands for chronological signature. And the aim is to design a triage tool to help clinicians and patients to get the right patient to the right specialist team. What does it mean? In mental health, there are certain specialist teams, like, for example, eating disorders, depression, or for example, a neurodevelopmental condition or psychosis. And when a patient is being referred to secondary mental health, there is a triage system, and this patient should be sent to the right team. Just imagine if someone with eating disorders will be sent to psychosis team. So psychosis team are not dealing with mental health, and with eating disorder, what they will do, they will push back and send back the patient. So and then patient, or for example, they think, oh, probably. So the psychosis team can refer this patient to eating disorders if they're confident that this patient belongs to eating disorders team. However, there might be quite complex cases where one of the specialist team may not be sure which team is the best suited. So the patient becomes kind of in limbo, or what's called a hidden waiting list, where the patient is being bounced between different teams. And just imagine if someone with really acute psychosis and being sent to accidentally or mistakenly to depression, because psychosis, it's really multifaceted a problem, and it could be, for example, it was for whatever reason was wrongly sent to incorrect team, and of course it takes time to re-refer a resend. However, in psychosis, especially acute psychosis, the patient should be treated within 14 days, because otherwise the patient becomes really unwell, and usually such patient they end up in emergency department, which is far from ideal for such patient for many reasons. Or even such patient, they end up in a very poor situations. And so we developed a model where we inject the patient history plus new referrals if patient is known, or new referrals, and based on this referral we can recommend. It's a so framing in computer in machine learning terms, we call it a text classification or chronological text classification. So the system was predicting probabilities where the patient should be referred to, plus we provided some explanations why the model thinks that this particular patient with such particular history should be referred to a certain team. And another project we worked on, we used an information extraction tool to put a nice and validated suicide prediction tool or a suicide risk, well, not prediction, suicide risk estimation tool to use with electronic free text record. So this risk tool, it is a validated tool, was developed several years ago by our colleagues, clinician psychiatrists. You can Google, it's called OXMIS, so mental illness and suicide. And this tool was developed using structured and epidemiological data fields, such as, so for example, history of violence, the use of different medication, parental suicide. So all this information as input to the tool is well coded. However, we've been tasked with the question, can we extract this information from free text nodes? And then we can structure it exactly as we do here. So basically, we've been asked to convert free text chronological records into structured tables, which are in the same format as the tool can ingest. And we trained the model. It was collaboration, so we were able to some degree to work with the tool. Now it is being studied in more details. On another note, we developed a tool, and this slide is to show you the complexity of an annotation schema. We've been working on a tool to extract information to structure clinical notes on depression. And we developed a very large annotation schema where we ask clinicians to highlight a wealth of information such as diagnosis, history, symptoms, health scores, a medication, a prescribed responses to medication, side effects, adverse effects, then temporality, experience or who experienced. It was very, very large. And as you can see on the left-hand side, we used, it was several years ago, we used a kind of some interface, but it's very versatile and nice interface where you can highlight. So there are drop-down menus where you can choose the item you want to annotate for, and clinician, they sat down and annotated data. And just a couple of brief words about the importance of a good annotation schema. So in order to develop a good information extraction tool, the annotation schema should be really technologists and clinicians, they should agree and they should work really well on the annotation schema. So agree on things, because the way annotation schema will extract vague data and putting rubbish in, rubbish out, as we all know. This is just to highlight the importance, and in some cases might be quite complex. And usually we start with simple annotation schema, then hierarchically we go down and we make it more complex. And now I want to move, so aware of time, I will move to more new and exciting tools that people started using, which are called large language models. And just out of curiosity, I went to PubMed and I put how many publications came out with the word of ChatGPT. Obviously, before November 2020, when it came out first, it was 0. Last year, in 2023, there was almost over 2,000 publication came where people wanted to explore. And as of last week, already people have done almost more than half of the whole year, and I anticipate it will go far beyond what we see. Obviously, there is lots of interest in using LLMs, and for a good reason. So every day, every week, there are more and more papers coming out, and if you look and you follow Twitter, Hugging Face, or people quite influential in this area, and you see a really zoo of all sorts of models that are popping up, and it's very difficult to follow up, but there is a massive progress is happening in this space, and especially as a mixture of experts, models like Mixtral and others. So why LLMs are useful? There are lots of, I'll go briefly because perhaps the majority of you are familiar with this. So first of all, we can leverage LLMs for information extraction. So, we can do some fine-tuning, like instruction-based fine-tuning if you really need. But I tried GPT-4 and I put a very simple, without any prompt engineering, LangChain, or any fancy technologies. I asked simple, please extract information from this and organize in a table. And as you can see, it did a pretty decent job. Well, really precise job. So we don't need to train any NER model. We don't need to train any relation extraction, a classification, so negation, and so on and so forth. And if you master your prompts and you do a bit of tinkering with this GPT, especially 4, it does quite good work. So the LLMs, apart from information extraction that they work quite well, another good use is to summarize long text. And obviously, clinicians, when they see the patient for the first time, or for example, this new clinician who picks up on some patient, they start reading through patient history and trying to pick up some certain keywords like hospitalization, certain drugs, condition, and so on and so forth. However, it's quite lengthy and they may miss, especially, it is Friday night or early morning on some beginning of the week, or they've been doing 24, 26-hour shifts. Obviously, there is some human error could be done. So summarizing, but meaningfully summarized documents is extraordinarily helpful. And lots of companies, startups and big companies and research groups, they work on text summarization, clinical text summarization, including the estimation or comparison the errors made by humans and both the hallucination by machines. And more the next frontier where LLMs shine and could be used nicely, it's speech to text. So for example, when clinicians, they see and when they interview patients, they take notes and then they write. Then they take notes and then they have to write. So it is really time consuming. So if we can optimize this process by recording sessions between clinician and a patient, and then we can transcribe using all sorts of methods, it will save lots of time to clinicians. So clinicians may pay more attention to patients, so there is no burden. However, also then, so once it is all transcribed and written in text, and hopefully it will, under the assumption it's all validated text, we can then run NLP method to extract symptoms, for example, mental state, or we can use some phonetics or linguistic patterns to understand mood, complaints, and so on and so forth. So imagination is really not limited. So you can see a huge potential for LLMs. So LLMs are really great engine to transform speech, both text and semantics, and phonetics and linguistic patterns, voices into meaningful, hopefully meaningful features. So there is another work where LLMs shine is in generating synthetic data. This is one of the works we did with our team. So it's called Detecting the Clinical Features of Difficult to Treat Depression using Synthetic Data. So difficult to treat depression, it is a case where clinician tried many approaches. However, the patient doesn't feel any improvement. This is really debilitating, and it's really unpleasant situation when nothing helps. So clinicians are trying to come up with other approaches. If they could use a mixture of different drugs, antipsychotics, antidepressants, they can use cognitive behavioral therapy, and so on and so forth. So there is a lot of interest also in pharmaceutical companies to identify cohorts of such people in order to invite to clinical trials. And it's also called so what we did to identify, however, in order to identify difficult to treat depression patterns, it's also really tricky because there is no there are no one-to-one rules, or there are no clear rules. It's all very subjective and based on some clinical expertise and experience, it is well documented, but still some clinicians may even disagree on what does it mean, difficult to treat depression. Some people may think, oh, if for example, if a clinician tried 3 different antidepressants within a year and there is no improvement, probably there is something is going on which doesn't respond nicely. Nevertheless, I don't want to delve into the clinical aspects of this work. So what we did, so we use a ChatGPT. We worked with clinicians, so clinician designed a prompt to generate synthetic documents, and we trained a model. So we use both a GPT-3 Turbo and also 4. So we generated 3,000 fully simulated notes containing examples and describing positive and negative features of DTD. So whereas mean positive and negative, it means there is a clear sign that the person doesn't have difficult to treat depression. There are clinical criteria, so the person doesn't meet clinical criteria. On positive, it means features or representation clinical notes that support the presence of DTD. So for example, it could be written like, so this patient has been known to services for 10 years. We tried 25 different antidepressants. Unfortunately, we do not see a remarkable improvement. So this clear sign that something is going on and the treatment is inappropriate or something. And then, so the clinician, they extracted spans. So we designed a tool to annotate documents, and clinicians, they sat down and they highlighted specific text spans which correspond to such features. So for example, it could be like age-related factors. It could be substance abuse. It could be written. So for example, the patient used to drink 5 pints of beer every day. So it could be signs of substance use and others. So for example, a patient has tried 5 different antidepressants. So this span of text will be an evidence of such factors. And then we split, so we split the model to train, and then we tested on real data. So what we did here, conceptually, we designed, so we asked GPT to generate 3,000 documents. We trained the model on synthetic data and then applied to real HR data, because obviously we cannot apply GPT to real electronic health records. So this is schematically what we did. So we used prompts. We did span annotation with GPT, and we trained the model. And so, you know, like patient recalls being severely bullied at school. So this span corresponds to positive evidence of potentially contributing to difficult to treat depression. So we extract such spans. We train the model outside of this of electronic health records. Then we copied the model to the trusted environment where real world electronic health records are, and we moved and then we tested the model, and the model was performed not bad at all, specifically for certain categories. And if you wish to read a bit more, so there's a shameless promotion of our work. And now the question is, are HR help useful at all? So the idea and the hope of all of us and technologists and also clinicians is to develop really fancy AI methods, regardless of the technology under the hood, to parse or to extract information from electronic health records and to design smart and cool tools we can use both for clinicians and for patients as well. So, you know, we can use tools to identify patients, we can predict certain conditions, we can stratify for clinical trials, we can do lots of interesting and cool stuff. And this note is adapted from my colleague, Professor Dan Joyce, from his presentation. So he kindly agreed to give the slide. However, if you refer to the big data paradox, there is a very interesting observation published by Xiaoli Meng in 2018, a statistician from Harvard. It was very interesting. So the big data paradox describes a counterintuitive phenomenon that can arise when dealing with large data sets. So the paradox states that if the amount of data increases, the potential for accurate statistical inference or prediction can sometimes decrease contrary to the common belief that more data always leads to better results. Unfortunately, we don't have a time to delve into the statistical properties of big data. However, just briefly touch, just to give you some hints why. So first of all, we accumulate a lot of noise. So as the size of dataset grows, the amount of noise, irrelevant or misleading information can accumulate, making it more difficult to extract information. So the paradox of larger sample size states that so for example, the data quality decreases because sometimes large data set that accumulate or they encompasses small data sets with intrinsic properties. So basically you're bootstrapping problems and biases. And of course, quality and quantity trade-offs. So if you start gathering more and more data, and by the way, this is what we've seen with large language models when you first started training, like GPT-3 with 176 billion parameters on the whole internet. And then just people realized if you filter down and create a really clean and nice data set, and really high quality data set, you can use a less complex one, like with 7 billion parameters, like Llama, and they can perform part of a large models that trained on. So the big data paradox is not unique to healthcare or something. It's really statistical observation, and I really invite you to look at the links I provided here, and some of them just to put things into a bit of the context. So if you read this paper by Bradley, underrepresented big survey significant overestimate US vaccine uptake, published here. So if you can watch later this recording, you can go to the paper. But the bottom line is a survey of 250,000 respondents can produce an estimate of the population mean that is no more accurate than an estimate from a simple random sample of size 10. And that's really interesting. So from a statistical perspective, really interesting. So when you think that you can solve all problems by applying GPT-4 or GPT-5 with infinite number of parameters to whole your electronic health records, so please think carefully what exactly you think. And it exactly brings us to the problem, what we already see. And I think it's really interesting just to mention to enthusiasts among us where we want to see. So the clinical data, so the problem with EHR, they are not exactly fit for purpose. So EHR data, these are medical and legal narratives that collect information about patients. They're not designed to collect data that could be used and also could be used for proper research or epidemiological research. So it doesn't mean we cannot extract, but we should be really careful what we're aiming for, what we want to extract from electronic health records and to what extent they could be useful, because applying really powerful methods, we can start pulling out some spurious correlations which are not really meaningful. So, and we can find kind of the superficial artifacts which are pulling out. And I'm happy to extend this this idea of so EHR, they are great, but they're not designed to collect meaningful data for research purposes. And this is exactly brings us
Andrey,
to
I'm
ethical
sorry,
considerations.
I'm sorry, we have just a couple of
5 minutes
left, and maybe we want to leave some time for questions. So
yes. Okay, so I will just cut it down, and I just literally have 2 slides more left, and I will just go briefly, and because it just pretty nicely flows into what I want to conclude. So ethical problems. So the ethical, so we have algorithmic bias, and we've heard lots of things like where people designed a system that underperformed, or their prediction disadvantaged certain groups, like, for example, Black people in the US, or, for example, like gaydar to identify sexual orientation from people. And there are many, many more. And, well, I will skip on this, but there is what we found. There are intrinsic biases in the EHR system, that EHR system are not designed to collect data for modeling properties. And if you keep using biased data, it will simply lead to really biased results. And this is why we also need to involve, it's called a participatory design, but we need to involve patients and people from from different representations, and to understand their voices and opinion on how we design system. Probably we are not. Probably what we are trying to solve problems that are not relevant, or these problems they may pose some threat to people. So we designed. So there is a website you can look. So we are starting a new study. Also, yet another shameless promotion. So what is acceptable and what not unacceptable? What is unacceptable in data collection? And I would like to conclude. I appreciate it. Just overrun. I want to conclude my presentation by create a quote by Phil Agar from his book that. So the system we're designing, first of all, they need to be relevant to the actual social dynamics, or to and also they need to be relevant to the lives of the people they affect. So all the system we are not doing for fun. We should be always conscious of people sitting there behind the screens, behind the dashboards, and understand what they feel, their perception of such tools, both clinicians and patients involved. Yes, that's it. Thank you.
Thank you, תודה רבה. יש פה
תודה.
כמה שאלות בצ'אט. בוא נראה אם יש לנו זמן.
כן,
שאלו
is it published?
אם
Can
אתה
we
יכול
see the
לפרט.
app here? בסדר, אני אקרא תודה מילה. Is it published? So, אז אני מניח שהשאלה פה זה בטח אפשר בהתחלה לגבי ה-True Colors, הפלטפורמה שאנחנו אוספים נתונים. כן, חלק מהדברים כן. אני יכול, פשוט תשלחו לי, שנייה, אני אשים פה את המייל.
אני לא יודעת אם מי ששאלו הם עדיין בשיחה, אבל אנחנו יכולים, אם אתה תשלח בצ'אט, אנחנו אחר כך נפרסם את זה ביחד.
כן.
עם הפרסום של ההקלטה. והייתה כאן גם בקשה לשים לינק, the right patient to the right medication to the right patient.
כן. טוב, אני אשלח את המייל, כן, אני אשלח את המייל שלי.
אז אנחנו נפרסם.
אני אשלח, כן מילה, אז אני אשלח לך את הלינקים, סליחה שאני מבקש לעשות, אני פשוט לא יודע איך אפשר לתקשר עם כל האנשים שיש פה, אבל אולי דרכך אפשר, או נגיד שתוכלי קואורדינט דברים, כן. כן, יש עוד שאלה פלושת, לינקים בין שלי, כן, אם יש עוד שאלות, אז אני אשמח לענות.
אם יש גישה לאפליקציה מהארץ, או שזה רק ב-UK?
בינתיים זה רק ב-UK, זאת אומרת שאין לנו, אבל זה יכול להיות מעניין שגם כן לראות, אבל זה עדיין, אנחנו עובדים רק באנגלית בינתיים. כן, תודה.
שאלות
שנייה. יש עוד שאלות, אולי יש איזה דקה או משהו. אולי אני אשלח לינק לאתר של פרופסור אנדרי צ'יפריאני, שהוא בעצם, זה מעבודה שלו, שנייה אחת, אז יש שם מלא פרסומים שזה בדיוק על שנייה אחת. בסדר, פשוט חבל על הזמן, לא רוצה פשוט לכמה אנשים, אז אני אעשה את זה אחר כך במסודר, אני אשלח לינקים. כן, או אם יש איזשהו שאלות, אז אני ממש אשמח לדבר על אנשים, יש איזשהו משהו הערות או רעיונות, פתוח. ותודה לכולם.
תודה רבה לכולם שהצטרפתם, ותודה רבה לאנדרי שהקדשת מזמנך ונתת לנו סקירה מאוד מעניינת ומקיפה. ואנחנו נתראה באירועים הבאים. תודה רבה לכולם ולילה טוב.
תודה רבה.